Okay. So you can see me. So welcome everybody to the lecture. We are discussing Gröbner bases. And last time we learned about the S polynomials and about the criterion, how to detect whether a given system of polynomials is a Gröbner basis. So maybe let me recall the salient feature. So we're talking about S polynomials. What is an S polynomial? Okay, sorry. So what do I have? I have two polynomials, f and g. And I want to define the S polynomial. It stands for syzygy polynomial. And what we want to do, we form a linear combination of f and g with polynomial coefficient such that the highest term is killed. And the way to do this is as follows. Let's just say LCM is the least common multiple of these polynomials. So this is a right, sorry, of the leading terms, of these polynomials. Yeah. So I take the leading term of the first one and of the second, take the least common multiple. Okay, and then what I do is this. Okay, I multiply f with this least common multiple divided by the leading term of f. On the other hand, here I do the same, but with the roles of f and g exchanged. Okay, and then I notice that these two polynomials have the same leading terms. Okay, and then I also make a little adjustment, so they have leading coefficient 1. So I divide here by the leading coefficient of f. And here I divide by the leading coefficient of g, and then I subtract. And this is called the S polynomial. Okay, and the point is the LCM cancels, if you understand. Okay. So, okay. So this was important in the theorem. So we had the following theorem. I also recall that. The theorem was the following. I had the polynomials. What did it say? Okay, a collection of polynomials, G1 up to GS, is a Gröbner basis. Okay, maybe it's in a polynomial ring. So this is a Gröbner basis. I just say G basis to save some space. And this is if and only if the following holds. For all pairs ij, the S polynomial of Gi and Gj reduces to 0 modulo G. Okay, so this is a condition we can actually test. We can compute the S polynomial and we can do the division algorithm to check this, right? Okay, so maybe about the proof, okay? There was one easy direction. It was this. Namely this, maybe let me recall that. So why is that direction true? Well, the observation is that the S polynomial, if you look here, the S polynomial, of course, lies in the ideal generated by f and g, because it's a linear combination of f and g. So I see that the S polynomial of Gi and Gj lies in the ideal generated by G. So, okay, sometimes I use round brackets and sometimes brackets like that. Right. And then we learned if you have a Gröbner basis of an ideal, take any polynomial in that ideal, then it will reduce to 0. Okay. Okay. Okay, maybe I don't have to write that. We proved that. And the other direction is the more difficult one. Okay, and we proved it modulo a lemma, which I called the canceling lemma. And I still have to prove this canceling lemma. Shown via the canceling lemma. Okay, so I don't enter this proof anymore. It was a little bit complicated. But what was this canceling lemma? Okay, kind of captures the essence of what can happen when you cancel terms. So here is the canceling lemma again. Okay, so I have a collection of polynomials, G1 up to GS, non-zero. And I have terms. Okay, and T is also a term. Such that, okay, the following holds. The leading terms of all these products, T, I, G, I, they are the same. Okay. So they have all the leading term, and now I take a linear combination. So let I take coefficients such that when I form this linear combination, okay, the term T cancels. So I can express this by saying the leading term of this linear combination is strictly less in T. So I should say we have of course, a term order is always chosen. All these notions make only sense with respect to a chosen term order. Okay, so this is, I have the canceling of T. Okay. Then the point is now, if this happens, then one can show that this polynomial is actually a linear combination of the S polynomials of the G's. Okay, so then there are some coefficients, lambda JL in K, such that, okay, this can be written, so let's say the sum over J less than L. I have these coefficients. I have this UJL. I define in a second what it is. And here is the S polynomial of GJ and JL, where JL, what is it? It's T divided by the least common multiple of the leading terms of GJ and GL. So I know this is quite technical, but that's how it is. Okay. Moreover, the leading term of what we have here is less than T. Leading term of this product less than T. So this is the canceling lemma. Okay, so in a way, you have this sum lambda I T I G I. Okay, so it is already a situation. All this, they have all the same leading term, but it cancels. Then you can rewrite this as a linear combination of polynomials of some very specific polynomials that we can control. Namely, we can rewrite it as a linear combination of the S polynomials. The S polynomials we can compute, okay? And we have this, that the T doesn't occur anymore. Everything in this new linear combination has terms strictly less than T. Okay, the proof is not difficult, actually. It's just a statement, is a little bit technical. So let's prove it. So some notation. Let's say mu I is the leading coefficient of GI. Okay, then I can say the coefficient of T in this linear combination that we are studying equals this, namely lambda I mu I. And this is 0 by assumption. So this here expresses the canceling of the term. Okay, so what do we do? Some more notation. Let's introduce the polynomial pi. So what is that? I have tigi and I divide by mu I so that the leading coefficient becomes 1. Okay. So this thing somehow looks like, in a way, I mean, this looks like t plus, okay, lower order terms if you want. I didn't use this before, but this is what I mean. I have now the leading term t with coefficient 1 plus lower order terms. Okay, this is very intuitive. Okay. And right. So and then I define that I look at the differences. Actually before doing so, so maybe okay, the thing is, so what helps me usually is a little picture. So I put here a column of polynomials, P1, P2, P3, up to blah, 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 PS minus 1, PS. So these are all the polynomials that are relevant to us, okay? I will take a linear combination of them. But they have all the same leading term. Okay, so I mean, I can express what's going on more succinctly by looking at the difference. So I just define the difference of these polynomials and I call them Q. So put Qi as the difference of Pi and Pi plus 1. Okay, both. Right. So, and then it's very easy to see. Okay, I think probably clear from the picture. How can I reconstruct like the p's from the q's? Okay, and I write it down. This is just the sum of the pj is qj plus qj plus 1, etc. I go up to qs minus 1 plus ps. So I think one can see it here. If you, okay, ps minus 1 you obtain, you just take qs minus 1 plus ps. But if you go higher up, let's say you want to express ps, you just have to add all these q's, and at the end you add ps. Okay, I think this is quite easy. So in a way, if you want, it's a telescoping sum if you write down what it is. Okay, so now what can we say? We are interested in this linear combination. Okay, so I can rewrite it as lambda j mu j pj. So that's what we want. Okay, and then now I plug in, I express the pj's in this using that. Okay, I use this, plug it in here. I exchange the order of the summation, and then I get this. So maybe I don't give every step. After changing the order of the summation, I have this. You check the details yourself. Okay, here I have lambda j mu j. Okay, I can take this out, qi, so that's why I exchange the parentheses. But then I have a contribution coming from the ps, and this is the contribution. Okay, and now you see the point is this is 0. So this contribution here goes away. And my polynomial of interest has now been expressed as a linear combination of the QI of these difference polynomials. Okay, and all that remains to do is to show that these difference polynomials QI are linear combination of S polynomials. Okay, actually, yeah, that's what I will do. Actually, I will show that the QI is a multiple of an S polynomial. Okay, how do I do it? Show that. Okay, I write down what I want. We'll show UI actually in the general statement, you know, it's very general. It's sum over J comma L, but I will assume L is J plus 1. That's enough. It's enough to look at consecutive pairs. So I showed this is okay. So maybe let's put a star on. Okay, and then let's see when I've done this, then I'm finished. Okay. Okay. Actually, this is clear. Then I'm done. Okay. Okay, then I'm done. Sufficient to show actually. Okay. Right. So how do I do that? Actually, I think it's more convenient to write it down in a little bit more generality than have a little bit less indices. So, okay. Let's say maybe LCM. Okay, sorry. LCM. I fix J and L. Let's say LCM is the least common multiple of the leading term of GJ and GL. Okay, I fix J and L. Okay, and then I write down, okay, what was the UJL? Is T divided by the LCM. So if you remember, this is here. This is the definition UJL. Okay. Okay, now I can write down, I know it's a little bit technical. I'm sorry for that with all the indices. But this is the 1 over UJ, the LCM, divided by the leading term of DJ minus 1 over mu L LCM divided by leading term of GL. So this is what I wrote here is exactly the formula with which I started. This is this formula. Okay, here, just this formula. Instead of F and G, I say GJ and GL. It's exactly that. Okay, good. So, but then you see, if you look with closer what this is. Okay, actually it's best to multiply now with UJL. Okay, what do I get? The way this is constructed, I get exactly this. This is J, here I have an L. Okay, so it's exactly that. And this is PJ minus PL. Okay, and I'm done. Okay, so this is the proof. So actually these proofs, when you write them down, it's really ugly with all the indices. But if you think about it, or maybe look at an example, and so you see it's really simple. I mean, there's not much happening here. Okay. Right. Any questions on that? Okay, doesn't seem to be the case. Okay. Okay, so if I want to, let's say I want to test whether I have a Gröbner basis, then I look at all the S polynomials of pairs and I make a division with remainder. But in some cases, you don't have to do this. There is a case where it is, okay, there is a situation where one can immediately see that the S polynomial here reduces to 0. And this is the case when the leading terms of F and G are coprime. Okay, so let's prove this. Okay, so we have a theorem. Sometimes it's called Buchberger's criterion or Buchberger's first criterion. There's also a second one, Buchberger's first criterion. Okay. So Bruno Buchberger, he had introduced this concept of Gröbner basis in the 60s in his thesis, and he named it after his PhD advisor, Wolfgang Gröbner. Okay. Bruno Buchberger. And so what does it say? Suppose F and G, okay, are polynomials, of course, in many variables with coprime leading terms. Okay, then it turns out the S polynomial reduces to 0 modulo what? Modulo F and G. So this means if you have a collection of polynomials, you want to test whether you have a Gröbner basis. For those pairs of polynomials with coprime leading terms, you don't have to do any work. You know immediately it goes to 0. Okay. Very useful. Okay, so let's prove it. So let's give name to the terms of these polynomials. Let's say f is the sum lambda I ti. I goes from 1 to p. And g is the sum j from 1 to q, mu j s j. With terms, okay, that are ordered. So Tp is greater than Tp minus 1, etc. The same with the Qs. Terms. And coefficients. Non-zero coefficients. Otherwise, I don't have to write them. Okay. Okay. So we have to write the S polynomial. What is the S polynomial? Of F and G. So maybe the LCM that we have to consider of the leading terms, okay, you understand. The LCM we have to consider will be TPSQ. Okay, so it's very simple here. Okay, I have to correct my coefficient. And here I have SQF minus mu q to the minus 1 TPG. Okay, so this is, you check directly that this expression cancels the leading term. Okay, now what is special about this? Okay, let's write it again. Maybe multiply with these coefficients. They are a bit of a nuisance. Actually, one can assume that they are all 1, the leading coefficients, to save work, but okay. Not important. Let me write down explicitly what we have. Okay, what is here of interest is, I mean, I plugged it in, but you see the sum only goes to p minus 1 and q minus 1 respectively because I have this canceling. Okay, good. So the terms. So what, now let's have a look at the terms. What terms do appear? Okay, the terms appearing. I claim they are pairwise distinct. So what are these terms? So I have SQ, maybe I write them. I have SQ T, right. In which order shall I write them? Maybe I start with 1, SQT1 up to SQTP minus 1 and TP S1 to TP SQ minus 1. Okay, are pairwise distinct. So this is important. Let's, oops, what did I do? Ah, yeah. Okay. Okay. So why is that? This is a consequence of our assumption. Okay. Let's check. Let's check why this is okay. Okay. Assume it were not the case. So we had SQTI equals TPSJ, because it's clear among there, of course, they are distinct, We just have to check that a term here must be different from a term over there. Okay, so then what can we say? Okay. Okay, what do I want? Okay, I want to write maybe the least HCM of TP. Maybe I write it this way. Okay, now I have to think. What did I want to say? Okay, I look at the, okay, in general, the least common multiple of TP and SQ, okay, must divide this expression, okay? This expression is a multiple of TP and it's also a multiple for SQ. So I must have this. But by our assumption, because the TP and SQ are coprime, this is TP times SQ. Now I see TP divides TI, and this implies that in our term order, TP is less than or equal to TI, and this is not possible, okay? Because TP is the largest one. The largest one. Okay, so it's here where I use the assumption of the coprimeness. Now what do? We want to show that this expression here reduces to 0. So
A
what we
short
got?
question.
Yes, sure.
That the least common multiple really divides that. I'm not sure because TP is actually greater than TI, right?
But you see, my argument was this. You see this term.
Yes.
So this term is a multiple of TP, and it's a multiple of SQ. Yes. So therefore.
Okay.
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 Okay. Right. So I look at this expression, and I want to show now. I mean, I want to reduce to 0. Okay. I want to do a sequence of reduction steps, which will remove all this. What? Okay, I have to think. Which will I remove? Yeah, I think I will remove all these things. And how do I do that? Okay, let me write the plan, because I cannot write everything down, that otherwise will be a little bit messy. Okay, we add, we successively add. Okay, these polynomials, mu1 s1 times f, u2 s2 times f, and so on, uq minus 1 sq minus 1 times f. Okay. Okay, we add two, okay, this is clear. We start with the CCG and then we add this. And the point is, every of this addition is a reduction step. These additions is a reduction step. So why? Okay. It is a little bit delicate, actually. So what do we do? Okay, let's first look. Let's have a look at the first one. Okay, here is our S polynomial. And right, so but I have here, in this polynomial, there appears the term SQ. Let me. Okay, so here, the leading term of this, maybe I can write it here on the side. The leading term of this thing, maybe let's do it in color. So I look at this. The leading term is this. TP. Okay. And this term appears here. Okay, if you look here, I can put it, make it orange. Okay, because in this sum, the first one has this. Okay, it has TPS1. Okay, so when I do a reduction, if you remember how do we reductions with these polynomials, I need that the leading term here of this, here it is. Okay, I have this, and you pick a term that is divisible by this leading term, and that I have this term. Okay, and then you add. Okay, you add this. Actually, you add this multiple of f mu1 s1 to this, and this way you kill a term. Okay, so this is what is allowed by our definition of reduction. I don't want to write this formally, but I hope you can understand. Good, but the question is, can we go on like that? Okay, we want to now go on with the next one. And the next one, maybe green is nice. The next one would be that. And I want to continue. But there is one thing I have to consider, that when I add, you see, when I add this thing has lots of terms, okay? And this, what I have here, is just the leading term. The leading term I kill, but by doing this, I add lots of other terms. And I have to make sure that these terms that are added don't mess up my picture, okay? Right, but all the terms, so maybe I can make a drawing. Let me make a drawing to illustrate what's going on. The way I see it is this. Okay, let's write this TPS1. Okay, this is just an intuitive writing of the terms of this second contribution. And this is when I write them up, meaning the higher I write them, the higher, the bigger they are. Okay, so I've written all the terms, they are here. Okay, and this is This is the, let's go back to the orange one. This is the one that is going to be killed. Okay, right. But when I kill it, okay, I kill it. But here, the other terms, I mean, I don't know, you see, terms are added, the blue ones. Okay, but all the blue ones, they are smaller. Okay, they are smaller. Fine. But there is, we shouldn't forget the terms that I have written here. These are the ones of this guy, but they're also the terms of this guy. Okay, so maybe I can write them here on the side. So maybe I write them here. There SQT1, SQT2, blah, 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 SQTP minus 1. They are here. I see them like as a different column. And so what's the point now? We know, I mean, those here, they are disjoint from this disjoint. So, right. So now I have to, actually, what do I want? Okay, what do I want? Let's see, when I want to go on like that, next, I want the next one to be killed would be that one. To be killed next. Or cancelled next. Right. I have to make sure, but I have to make sure this term is still there. Otherwise, I cannot kill it. But it will be there because you see, the red one is bigger than all the blue ones. And these on the left-hand side, I mean, they cannot interfere. I mean, the red one, the only way it could not be there is that this red one here would also appear somewhere here. But this is not the case because of the disjoint. That's all, okay? Maybe I exaggerate, but that is the point, okay? So maybe I let me write a little bit more. Every of these additions is a reduction step. Then, because after adding, I do it in a certain order of these guys. Say I do the first J ones. The terms as J plus 1 F TP actually up to SQ minus 1 TP are still there. Okay, so this is kind of the crucial thing that I try to explain by pictures. Okay, and then, but then everything is fine. So we obtain, okay, so here is the lambda p mu q as polynomial. Now we make a reduction. Actually, we only reduce modulo to f. We only add multiples of f. And what do we do? Okay, I first copy. So what I first write, I copy the first. So this is, if we go up, it's that one. Okay. And right. Okay, and then, okay, what I have is this. Okay. Maybe this needs another explanation. Okay. Right, so this I have after, okay, adding all of these guys here. Okay. I'm just thinking why there is the minus lambda PTP here. Give me a second. So, okay, I add these multiples to F.
May I ask a question?
Sure, yes.
About the lambdas, actually. I was wondering why, so we are adding mu1 S1F, and we want to kill the term with
The orange
S1
one.
TP.
Yes.
And in the S polynomial, we have the factor lambda P. So don't we have to add this term multiplied with lambda P inverse also?
Let me see. I think I know what you want to say.
So that the coefficients cancel.
Yes. Maybe I had, let me think.
But isn't the lambda P already in the F contingent?
Yes. So I thought it's easier. So instead of looking at the S polynomial, looking at the S polynomial multiplied with these two numbers. But anyway, for the whole explanation, I mean, I could simplify the notation by assuming lambda P and mu Q are 1. I mean, I could do that, and then I wouldn't have this mess with the coefficients. This is just the scaling. Okay,
but when we successively add these expressions, do we add them to S of Fg or
yes,
to
we start. Okay.
lambda P?
Okay, this is a good question. I think when I wrote this, we added not to S, but we added to that. I think that's what I wanted to say.
Okay.
I think that's what he wanted to say. But as I said, we could assume that those two are 1. Maybe I should have assumed that, and then the problem disappears anyway. But right, I think we start with that, and then we add and add and add. Now I try to explain, maybe you see it, what after this reduction, I claim that actually what I have added is this. So now the only thing I'm a bit puzzled, why do I have this? Let me think. Oh, yes, it's okay. No, sure. Sorry, I'm confusing myself. I mean, what I do is, I mean, in this procedure of adding, maybe you see, when maybe I rewrite, I have the sum. Maybe, okay, I say, you see, all of these things are added. So these are exactly these things. Okay, so I add this, and this here is, I mean, what comes from this second contribution. So I exactly have this. Okay, and the point is now, if you look closely, that, I mean, these two things are actually equal. I mean, this and this, they are equal. They are the same. So what we see here, this is actually this is, okay, let me write G times sum lambda I di I from 1 bis p minus 1. Okay, because, I mean, the green one I can factor out, and this plus this gives me G. So I mean, to summarize what you realized, the S polynomial is a multiple of G. Maybe I can write it. Thus, SFG is a multiple of G. Okay. And the multiple of G, now easy to see. A multiple of G you can reduce. Now this G times something, whatever it is irrelevant. It's just a multiple of G. You can reduce modulo G to 0. This is very easy to check. You just remove term-wise, okay? Okay, you take the leading one, reduce the multiple of G, kill the leading one, and so on, until you have 0. Okay, so this is the proof. Okay, right. So this was all a little bit tricky. Now let's see. Let's have some examples and some applications. Now it will be easier, okay? So this was like the hard part. So let's see what can we do with it. What can we do with it? Okay. So here, let me give some examples. So maybe example 1. So in every lecture in algebraic geometry, there is the twisted cubic. So let's look at the equations of the twisted cubic. So we look at the following polynomials. I have y minus x squared and z minus x cubed. So I have 3 variables, x, y, z, and 2 polynomials. This is the equation of the so-called twisted cubic, whatever this is. Okay, and the point is this is a Gröbner basis. This is a Gröbner basis. Okay, I have to say with respect to which term order? With respect to lexicographic, where the y is larger than the x. And the z is larger than the, okay, it doesn't, it's only important the y is larger than x and the z is larger than x. Because, okay, then, okay, under this assumption, then let me mark the leading term. In the first polynomial, it will be y. Okay, and in the second, it will be z. So these are the leading terms, and they are coprime. Leading terms. Okay, and okay, so I have only 2 polynomials. The S polynomial reduces to 0 because of our criterion. So I see this is a Gröbner basic without doing any calculation. You see, that's in a way nice. But let's continue with the example. However, let's change the term order. However, for the lexicographic order where x is larger than y, larger than z, then it looks different. So what, okay, maybe I should have. So now let's choose another term order. What is the other one? The blue one? Okay. For the blue term order, let's mark what is the leading term. For the blue term order, the leading term will be this, x squared and x cubed. And of course, they are not coprime. Okay. So we cannot apply the criterion. Okay, but now let's compute the S polynomial. S polynomial of f1 and f2. So this is f1. This is f2. Okay, how do I compute the S polynomial? Maybe let's do a side calculation, then you see how I do it. F1 is minus x squared plus y. F2 is minus x cubed plus z. Okay, then I multiply with x, okay? With everything, I multiply this with x, then I get here cubed, here I get x, and I subtract. And what I get is, so the x cubed is killed, and I get xy minus z. So, okay. So this is the S polynomial. And this is a normal form, okay? This is a normal form. Why? Okay, leading term is xy and is not divisible by x cubed and is not divisible by x squared. Okay, so this is a leading term, and so it's non-zero. Therefore, G is not a Gröbner basis with respect to blue term order. Okay, blue term order. So this, I think this is an extractive example where one can see the choice of the term order is really important. Okay. Okay. What we have seen here in example 1, we can easily generalize. Let's say we have the following. Let's say I have polynomials fi in the variables x1 up to xn, and consider, and I have additional variables y1 up to ys. These are variables, further variables, and the following polynomial: y1 minus f1, y2 minus f2, etc. ys. Okay, this is a okay. So these are the polynomials that arise when I study at the graph of the map given by the f's. Okay. And I claim this is a Gröbner basis. This is Gröbner basis. Okay, with respect to the lex order, where the y's should be larger than the rest. So let me, for instance, let's assume y1 up to greater than ys. What is important that the y's are larger than the x's. But to fix ideas, let's write it this way. Okay, I have this lex order. Then you see, then of course the leading terms are just here the y's, and they are coprime. Okay. Leading terms. They are coprime, and I can apply the Buchberger criterion. You see, this is really useful to have this criterion. Okay. Okay, and I have a last example, which I think is very good to make the connection to linear algebra. Yeah. When you have a matrix, then you learn, you do say you do row operations, and you bring then the matrix to a special form, to an echelon form. In German, it's called the Stufenform or Treppenform. In English, echelon form. And this exactly corresponds to Gröbner basis. So let me write this. Okay. Okay, to a matrix A. Sorry. So what kind of matrix is it? It's a S times N matrix over a field and a vector B, and K to the S. To a vector can assign, I assign these linear polynomials GI. So what do I have? Aij xj plus the constant term bi. Okay, A and B just encode this collection of linear polynomials. Okay, if A is in echelon form, term is called the Stufenform, I think it's called, or sometimes Treppenform, then G1 up to Gs is a Gröbner basis. With respect to legs, when I order as follows. The ordering of the variables is given by the numbering. So picture. So here's my matrix, and it may look like that. Okay, so it has this echelon form, and when I make a cross here, it means here I have a non-zero coefficient. Okay, so if you have this, here there is something. If this is A, okay. If A looks like that, then you clearly see what are the leading terms of our polynomials. These are just distinct variables. Okay, they are distinct variables. And so I can apply the Buchberger criterion, they are co-prime, and so I have a Gröbner basis. Okay. So you see here, I think this example is very important. So you see that this concept of Gröbner basis is very closely related to echelon form. And now, next, we will learn how can we actually compute the Gröbner basis. There is an algorithm for that is conceptually very simple. And this algorithm is closely related to Gaussian elimination. Okay, so it's conceptually very close. Maybe little warning just to, I mean, it's important to have this echelon form. For instance, if I would have x plus y and x plus z is not a Gröbner basis.
Question?
Yes.
In this example, shouldn't it be xi in the sum then, because otherwise
X. We are, okay, let me check. You are here or?
I am in the sum, yeah, exactly.
But the GI is the sum over J from 1 to N. AIJXJ. No, I think I want to have it this way.
But if you have xj, then you have okay, I don't understand, but okay, I have to.
Yes, I think it's okay.
Okay.
Simple example, x plus y, x plus z is not a Gröbner basis. Why? Well, Buchberg's criterion doesn't work. But anyway, you take the S polynomial. What would be the S polynomial is y minus z. Okay, the S polynomial is y minus z. And that's a normal form. You cannot reduce it. Neither y nor z are divisible by x. Non-zero normal form, so I don't have a Gröbner basis. Okay. Okay, maybe I should write with respect to this one. Okay. Questions or? So I would say Gröbner bases are really a nice concept with many applications. There is only one disadvantage. I mean, you had, I think in the exercise session, you learned how to actually compute it. So the most useful system is Macaulay 2. I hope you managed to run it on your note or on your computer. It's very easy to use. Okay, one can experiment and learn. The only problem is that often Gröbner bases, they can be very, very big. So not all, I mean, and the computation can take long, but not only that the computation take long, I mean, it can just be very big and the degrees can be very high, etc., etc. So this is not something you want to do by hand. you rather do it by computer, but even when you do it by computer, the computer may run out of memory quickly. So it's in German would say it's not ein Allerweltsheilmittel. I mean, even if we will see now many problems that we can solve in principle using Gröbner basis, but when you actually want to do it in practice, you may get stuck. This is very unlike linear algebra, where you can get very, very far without Gaussian elimination properly implemented or with properly pivoting. Here the situation is much harder. Okay, it's non-linear algebra. Okay, the next section is computation of Gröbner basis.
Still a short question. So
Yes.
are you sure if we take those polynomials and we really have all the variables x in each polynomial?
Again, which polynomials I take?
GI.
The GI,
and in
okay.
each GI we have all xj.
Yes.
Then
no, but what I mean is, you see, you are misunderstood. I assume
probably.
I say if A has this form, then the G1 has everything.
Yeah, okay.
But the G2 doesn't have X1.
Yeah, okay.
Etc. This is what I meant.
Sorry. Okay.
Okay.
Yeah, of
but,
course.
Okay, you are paying attention. So computation of Gröbner basis. Okay. So it's nice to have this umlaut in Gröbner. Of course, all the English-speaking people, the Americans, etc., then they don't know how to write it. Gröbner, Grobner, Groebner. Okay, like in my name. Sometimes it happens. So the idea is we fix a term order. Okay, I fix a term order. Okay, unreadable. To write it again. Okay, not much better. So, and I'm given a collection of polynomials. They generate an ideal, and I want to compute the Gröbner basis. So how can I proceed? So, well, what would I do? Let's say I have G1 up to GS. These are my polynomials. Well, I'm going to test. Okay, I pick I pick 2 of these polynomials, compute the S polynomial, make a division with remainder, okay, and see whether I get 0. When I get 0, I'm happy. Okay, nothing to do. If I get a normal form which is not 0, okay, then the idea is I just add this polynomial to my list. Okay, I add this. So I have increased, what I added is, in fact, I mean, the S polynomial is in the ideal. And if I reduce modulo these polynomials, I still have a polynomial in the ideal. So there's no problem. I just add this as a further generator, and then I continue. Okay. I always continue like that. I pick a pair, check. Okay. If I get non-zero, I add it. Okay. If I get 0, I'm happy. So this is a procedure. The only thing I write it down for me in the second one has to show that this procedure actually stops. So why would it stop? I mean, why does it go infinitely often? The reason is that we are dealing, well, it's a Noetherian ring, the polynomial ring. Okay, I will write down everything, but it's so easy to explain. So I have my generators, and what happens if I add, okay, if I add a polynomial where the normal form was not 0, then what actually happened, if I look at the leading ideals, I have increased my leading ideals, strictly increased. So in every time I add a polynomial to a list, I strictly increase the leading ideal, and we have Dixon's lemma. Dixon's lemma tells me every chain of such increasing monomial ideals must become stationary. So after finally many steps, this will not decrease anymore. Okay, the initial ideal will be fixed. Okay, and then this is the essential idea. Okay, to show that the algorithm terminates. So this is so simple, I can explain it without writing anything, but it's better to write. So let me write this as an algorithm, Buchberger's algorithm. Buchberger's algorithm. Okay, from 1965. So the guy became quite famous with his Gröbner basis, with his algorithm. So input, you have a finite set f, capital F of polynomials. Let's say non-zero. Output, a basis. Of the ideal generated by f. So the ideal, let me write with this parenthesis, such that f, okay, and the basis should be called G. Okay. Okay. So how do we do that? So this is like this pseudo programming you will understand. I begin my program. I initialize, initially G is the set F. And I have some auxiliary variable B, okay, which initially consists of all pairs G1, G2 that are to be considered, okay? So G1 and G2 are in F. Okay, I mean, it's a bit pedantic. Of course, they should be different. Otherwise, there's no point. And I mean, I can save some work. I can assume that the GCD of the leading terms is not 1. Okay, because if it were 1, I mean, they would be coprime and I don't have to do any reduction because of the Buchberger criterion. So this set is the set of all pairs that are to be considered. Now I have a while loop. While, okay, while this set B is not empty, we do the following. Okay, we pick in any way, you choose your way. It's not important now. I pick a pair, okay, in the set. I remove it. And UB will be the B without this pair. I have to write it this way. I remove the pair. Now, with the division algorithm, compute the division algorithm. The normal form H, so I denoted it this way. Okay, this is just, okay. The G is now assumed to be ordered list, so this makes sense. Okay, and then if, maybe I continue here. Okay, if this normal form is non-zero, then I will add it. Now let's do in the right order. Let's first update B. So I add to my set of pairs to be considered all pairs G, H. H is the new one and G is in G. Of course, I only have to add those where the GCD is not 1. It's okay, but if you actually implement it, of course, this is important. This saves a lot of time. So, and the G is also updated. I add to G, H. So I wrote it in this order because not the other way around. If I would first update G, okay, then it's not so nice because in the definition of the B, the G enters again. Okay, so it's better to do it in that order. So the idea is hopefully clear. H non-zero, I add it to my set G, I update, okay, I update B. Okay, this is the end of if, and if, maybe and if. Okay, That's, you understand, and if. And this is the end of the while. And then this is the end of begin, if you want. I mean, it's kind of. Okay, so this is the program. It doesn't really fit. Pretty simple, conceptually simple, easy to implement, of course. There's not much to do. Okay, now let's show that this actually terminates and works correctly. So I have a little theorem. It says the algorithm, this algorithm terminates and works correctly according to specification. So by this, I mean the output indeed will be a Gröbner basis. Okay, so proof. So I think this is the first time that I argue about correctness of an algorithm. So maybe let's be careful. Let's first talk about termination. Okay. So now note, in my notation now refers to what's happening in the algorithm. Okay, whenever in the algorithm, if I have an h computed which is non-zero, then the leading term of h is not contained in the ideal, monomial ideal generated by the leading terms of G. Okay, since H is a normal form. You see the algorithm here again. What was the H here? Okay, it's the result of division with remainder. So it's a normal form. And if it's not zero, being a normal form exactly means this. Okay, which expresses I cannot further reduce H mod G. Okay, so what I see, the ideal, hence monomial ideal, okay, will strictly increase. Okay, and by Dixon's lemma, which is another way of saying that the polynomial ring is Noetherian, Dixon's lemma says that this can happen only finitely often. Also, it can go, okay, may take many, many times, but it's finite. Okay. And then when we are at that stage, when this will not be increased anymore, when G will not be increased anymore, okay, will not be bigger, then what happens to the set B? The set B of critical pairs, set the set B is reduced in cardinality. Okay. In each step, because maybe go back to the algorithm. That's what happens here. Okay, but if you are in the already there where the G, I mean, no H will be added. Okay, Oh, here, sorry, I have to show here. No H will be added, so the B will be unchanged. But here, you see, every time I go on in the while loop, I take out a pair of B. But no more pairs will be added. So after finally many steps, the algorithm will stop. Okay. The algorithm will terminate. Okay, this is about the termination. This is not complexity, no cost, it just stops. How about correctness? Okay, every time, okay. If you, I mean, how do you show correctness of an algorithm? You have to write some statement which, okay, the algorithm assume has a loop, okay? Then you write a statement which is invariant in every loop, okay? And so you can make an induction proof, at least in principle. So, okay, I show that at end of every while loop, we have, okay, F is contained in G, is contained in the ideal generated by F, and for all G1, G2 in G, if the pair is not in B, so if it's an uncritical pair, then I'm sure that the S polynomial of these two polynomials reduces to 0 modulo the G. Okay, and of course the G, I mean the G is the one that changes during the execution of the algorithm, and also the B changes. Okay. Okay. So this we need to by the criterion. Okay, it's enough to show that. Okay, enough. By criterion for Grabner basis. Because if the algorithm terminates, the set B will be empty. Okay, if you remember. Okay. When you are out of the while loop, B is empty. No critical pair anymore. So therefore, then I know for all, okay, then I have to consider here all pairs. For all pairs, the S polynomial goes to 0. Therefore, by this criterion, I know I have a Grabner basis. Fine. Okay. So we need to show this statement here. Use a little bit of colors. The blue one. Okay. Show. Okay, by induction actually. Okay, induction. Then there's an induction start. And if you think about the induction start should be clear, hopefully. Why is it clear? Yes, it's clear because if you look at this we have, because F equals G. And this we also have because at the beginning B consists of all pairs. Okay, so this is good. Now the step, induction step. So we go from GB to G prime and B prime to have some notation. Then there are two cases. Case 1, H equals 0. Okay, so then in this case, G prime equals G. B prime is I remove from B the pair that I considered. Okay. And what do we need to check? So I removed a B. So now if I look at the criterion here, there is only one pair I have to check, namely this pair. I have to check this. But this is okay. True. Why is it true? Because h was 0. H was the normal form that you get when you division the remainder with this thing is 0. So it's good. Okay, and case 2, h non-zero. Okay, there's actually nothing to do. Okay, note maybe so I can write something. Nothing. What do I do? Maybe I go back to the algorithm. If you look here, h non-zero. So what happens with the B? I mean, B gets larger. So the set of pairs outside of B gets smaller. So it's trivial, nothing to do. Okay, let me just do this clear. I think this is clear. Or maybe, okay, yeah, let's be pedantic. Note. If I have this, and then I make my set G larger, that's what's happening. Then I also have this. So this is a trivial observation, but I mean, if I would write down formally, that's what happens. Okay, so this is the proof of correctness. Any questions? Okay, one should always do an example, but let me try to do an example. It's a little bit annoying. This is an example. Okay, one can do it by hand. It's still a little bit annoying. Most of the examples should be done by computer but this is a little example, and let me do it. I think it helps. It helps. Let's do an example. The example is this. I have these polynomials, f1 and f2. Okay, x 3 cubed minus 2xy. This is one polynomial. The other is x squared minus 2y squared plus x. Graded lexicographical order, x greater than y. So I only have two variables. Let me mark the leading term. Here it's x cubed, here it's this. These are the leading terms. Okay, so let's trace the algorithm. At the beginning, G is f. So maybe how do I write it? Let me write it different. Maybe at the beginning, G is f. B just has one pair, f1, f2. I compute the S polynomial. So it's very easy to compute. Yeah, but I'm a little bit out of time almost. So you compute yourself. The S polynomial is minus x squared. It's very easy. Okay. This cannot be reduced, as you can see. You cannot divide it by x cubed. You cannot divide it by x squared. So this is a normal form. So this is actually what you get when you do division with remainder. Nothing changes. Let's call this f3. So minus x squared is f3. I add it. So the new G will be G union f3. Okay, and the new B is, okay, I have now to consider the pairs f1, f3 and f2, f3. The pair f1, f2, I don't have to consider anymore because I did it already. Okay, so I have to consider these two pairs. Okay, now I pick, let's say, f1 and f3. I compute the S polynomial. Okay, I leave out the little computation. It's easy actually. It's minus 2xy. Okay. f2xy, this xy is a normal form, obviously. So this is actually the normal form. And I call this f4. Okay, so now I add to my set, this is the new G, I add f4. I update B. So let's see, what is the B? Okay, Lucy, maybe I can, maybe. So this is the one, just to make clear, the one that I removed is this, so let's maybe write it this way. So what remains is f2. Okay. I'm thinking the f2. Okay, let me first write and then explain. f2, f3, f1, f4, f2, f4, f3, f4. Okay, the f4 is added. 1, 2, 3. That's okay. That's all so what I have done, this one goes here, okay, and then I have it, okay, and then I added this. Good. Well, nothing to explain actually. So this is my B. Then, okay, let's say I take f2 and f3. I take it. Let me see. Did I do something wrong? No, sorry. I do S f1, f4. Okay, computation shows this is minus 2xy squared. Okay, and if I reduce this, now this is easy. You see, because I have here the leading term is x squared y, so this reduces to 0. Okay, so this is good. The f1, f4 is good. I can remove it. I remove the pair f1, f4 from B. Okay, then I go on with the 2 and 3. Okay, and now, you know, I save you the details. I take it, I reduce, and then one can check. This is minus 2y squared plus x. So this is the leading term. The leading term, y squared, I cannot reduce further. Not possible. So I add this, I call this f5. Okay. Okay, what will be the new G? I add f5. You see, it's quite boring, so it's really work for a computer, but I think it's helpful to explain. So B will now be, okay, why that? So I claim f2, f4, f3, f4. That's so, and f2, f5, f4, f5. So how do I get this? Okay. I'm almost done, huh? Let's see. Okay, here was my B. The f1, f4 was removed. Okay, so it remains and the f2, f3 is removed now. So what I have is f2, f4, f3, f4, and then I add it. Okay, I added the pairs with f5, but I didn't. I only added f2, f5, and f4, f5. But there are more f's. But you see, the f has this y squared. And the other ones, like for instance, if we take, for instance, if I would look at f1 and f5, I see the leading terms are coprime, so I don't have to add it. Okay, the reason I only add these two combinations with f5 is because the others combinations would have co-prime leading terms, I don't have to add them. Okay, now computation shows good for all, okay, for all Fi, for all pairs, Fi, Fj in B. One checks now by computation that the S polynomial reduces to 0. This is a computation. Hence, G, okay, the list F1 up to F5 is a Gröbner basis. For the ideal generated by F1 and F2. Okay. So this is a computation you can do by hand, okay? I hope it illustrates the algorithm. Are there questions? No questions. So, okay, plan for Thursday. And I remember last time I always said what we will do on Thursday, but it was a holiday. I didn't think of it. So we will now, next time on Thursday, we think a little bit about uniqueness. There is a notion of a reduced Gröbner basis, and it has the advantage that it's unique. For each choice of a term order, the reduced Gröbner basis of an ideal is a unique object, which is nice, and it's very easy to explain. Okay, and it's also, right, once you have a Gröbner basis, you just have reduces. That's an easy computation. And then we will learn, I will really want to tell you about all the applications. There are many basic questions in ideal theory, in polynomial rings, you can solve, at least in principle, with the help of a Gröbner basis. So there is elimination, computation of elimination ideals, intersection of ideals, ideal quotients, etc., computing polynomial relations. All of this, actually, conceptually, I mean, it's very easy to explain. I think this is very nice. So I really want to explain this, and I hope we can have some of that in the exercises. And when I'm done with this on Gröbner basis, we move on to the next chapter. In Natia MacDonald, we talks about modules, and then it will be abstract again. Okay.
I still have a short question if you have time.
Yes.
Could we
maybe shall
back?
I stop the video maybe?
But this question, we will, okay.
If you want, because maybe, good. You can still ask, but maybe, right. What is the question? I can go back to, I show it, but maybe we don't have to want to have everything of this thing of the video. Anyway, yeah. The file gets larger and larger and right, okay.
Okay, so could we go back there to the lemma or to the theorem where we computed some least common multiple to show some intermediate step? That was,
I don't exactly what you,
that was, just a minute. It was theorem Buchberger's first criterion.
Okay, good. This one
was, yeah.
Here we are. Here we are.
No. Buchberger's first criterion. Yeah, here. So here in one intermediate step,
in the proof of the theorem or what?
Yeah. In the proof, I still can't follow. I think why actually we get the contradiction there where we assume this equality.
Okay, you asked already.
Yeah, I asked about that, but I think
here.
I think if we have a least common multiple, then it is true that it is dividable by SQ and TP, but then it's another way around actually, not that way around, but another way around. So not the least common multiple will divide this, but this will divide the least common multiple. No, even that is not necessarily, but I don't think that the least common multiple will divide.
Oh, maybe, let me see, maybe you may be right. Let me check.
because it's actually.
Yeah, I see.
Let's consider some examples.
But it's okay. I mean, don't you agree if you have, okay, let me write it maybe here. Give me some color, but then I will remove it. So if I have, say, polynomials, I have A divides C and B. No, what do I want to say? Okay, then the least common multiple of A and B will divide C.
So now A divides C and B divides C, right?
And then the least common multiple divides C. Well, this is the meaning of least common multiple because the minimal even refers to the divisibility order.
The least common multiple will divide.
Do you agree about this implication, the green one?
I have to think about it a short moment. But the least common multiple is larger
Think of
than
numbers.
A.
Think of numbers.
It's
Think
larger than A and larger than B. Okay.
Yes.
And
Think
if it's larger than A and it's larger than B, then
okay,
no.
in German it's kleinstes gemeinsames Vielfaches. It's a multiple of A, it's a multiple of B, but it's the smallest in the sense, right? It's the smallest.
Yes.
But the statement is it's even the smallest in the sense of the divisibility order. That's why you have this. Think about prime number factories. If you factor these elements into irreducible elements, then you will see it.
Okay, maybe I have to think about it.
Think about it yourself. It's not difficult. But okay.
Yeah, probably not.
There are many details anyway. Okay.
I don't get why.
Right. So thanks for your attention, and then I see you on Thursday. Okay.
Goodbye.
Bye-bye.